We have seen together how to play with the trend, so how to remove a trend from a time series, because we know that trends are one of the main causes of non-stationarity for a time series. We have seen that we can use differences and we can use regression. Now, what we consider now is the problem of seasonality. So when our time series shows some seasonal pattern. Now, in a sense, a season is just another type of trend in which there is some periodicity appearing. So you can think of a sine cosine type of function that appears in your time series, and from a practical point of view, think of seasons like the seasons spring, summer, fall, winter. Why? Because think of looking at the time series of temperatures, you can expect, depending on where you are, but let's say that you are here in Switzerland with me. In Switzerland, you can expect temperatures during summer to be higher than those you can expect in winter. And this pattern will reproduce over the years. So you will have these temperatures that will appear and show this wave behavior over time. Also, from a financial point of view, we have these type of behaviors. So, for example, if you consider the markets, you know that we have business cycles, you know that you always observe periods of boom, then followed by periods of crisis. So you have seasons also in financial quantities. So we will start by dealing with seasonality here. As detrending is the operation that we use to remove a trend from a time series, deseasonalizing is the operation that we use in order to remove a season that, I repeat, is nothing more than a recurrent pattern in the data. So we always observe some sort of waving behavior in the data. Now, there are different ways in which we can play with seasons. The simplest one you can imagine is regression. So we can try to perform some sort of regression, and as we did with trends, the residuals of our regression will be our deseasonalized time series. Consider the time series that you see on your screen, the time series xt. Now, if you read this time series, what you see is that we have a component Wt, the white noise in our standard notation, around a cosine-shaped season. So what we can expect, looking at this time series, is to have a sort of cosine behavior, and around this we will have our white noise moving. Okay, so that will generate our time series. Now, this is exactly the same example that we will consider at the beginning of our practical lesson. But I think it is already interesting if you can spend some minutes analyzing this example. One thing that I want you to notice is that this time series here, since we know explicitly the form of the season, can be actually transformed in another time series that we can somehow easily estimate using regression. It is just a matter of using the properties of trigonometric functions. In fact, as you can see on the screen, we can easily rewrite our cosine seasonal pattern as the linear combination of two elements, one element in the cosine and one element in the sine. But this new representation is better for what concerns linear regression, as we shall see when we will estimate the different elements of this time series in our applied lesson. You can imagine that while fitting a linear trend or a logarithmic trend or any other type of simple trend is actually simple, coming out with a nice proposal for some sort of seasonal behavior is more complicated. So while regression is extremely useful and powerful, the weakest link, if you want, is the elicitation of a proper seasonal function. So a solution can be to use some automatic functions like the STL function that you find in R, but there are many more, you can imagine. Now, these functions do something very simple. They just fit several polynomials, they just fit several trigonometric patterns, and then they try to look for the best pattern that can explain, for example, the seasonal part and the trend part. Together we will see, for example, how to play with STL within the R framework. One thing that I want to stress is that very often, while this type of functions introduce a degree of simplicity for us because they increase our capability of quickly analyzing the data, it is pivotal to be able to read the results of the fitting. As I will show you in our practical example later on, it is very common to make errors and big mistakes in giving an interpretation of the results, for example, of an STL fitting. For example, as I will stress more and more in our practical lesson, the gray bar that you get in the STL representation of our time series is extremely important because it tells us what is the scale of the different components. And comparing the scale with respect to the original time series, for example, in this plot, you see that the trend that appears to be possibly important if you just look at the behavior of the trend. So you have this increasing pattern and then, okay, there is some more oscillatory part remaining. Yet, if you compare the size of the gray bars, you understand that the trend in this series here is not particularly relevant. In our previous lesson, I told you that another cause of non-stationarity in a time series are structural breaks. Like, for example, when you have a big jump in your time series because of some exogenous factor. Now, dealing with structural breaks is a little bit more complicated. In the simplest situation, so if you can really determine the reason why, you can, for example, introduce a dummy variable and take care of this big jump, especially if there is no substantial change in the time series before and after the jump, apart from maybe the mean value, because your time series had a mean value of, I don't know, 2, then after the jump it becomes 5. Okay, so if you can take care of this, it's not a big deal. The problem is that most of the times when you see a structural break in a time series, then also the properties of the time series change, because maybe from an autoregressive model of order 3 it becomes an ARMA model 2, 4. I don't know, I'm just saying, given an example. So what happens there is that the modeling is much more complicated, so we are not covering that here in this course. Now, what I want to do with you is to introduce some important models for time series, that is to say autoregressive models, moving average models, and their combination, getting the autoregressive moving average models, or ARMA models. Now, in order to do that in an efficient way and also to simplify a little bit the notation of different equations that we will see together, we have to introduce some common operators in time series. That is to say, the nabla operator for the differences, the backshift operator, and their combinations. So if we write nabla of xt, we are essentially writing down xt minus 1. So the nabla symbol applied to a quantity xt just defines the difference between xt and xt minus 1. The backshift operator that we indicate with capital B, conversely, is such that b is equal to b to the power 1 and b to the power k applied to a quantity xt transforms xt in xt minus k, so that if I just write b xt, this is xt minus 1. In other words, we can always write the nabla operator as 1 minus b. And in fact, by looking at this fact, we can write the d-order difference operator, nabla to the power of d, as 1 minus b to the power of d. So if you take the squared difference operator, so the squared nabla, so nabla to the power of 2, this corresponds to 1 minus b, everything to the power of 2. So it means that the result is 1 minus 2 times b plus b squared. And if you apply this operator to xt, what you get is the quantity xt minus 2 times xt minus 1 plus xt minus 2. Okay, so this is the way in which we play with these operators. As we shall see in a minute, the use of these operators simplifies a lot the treatment of time series. Now, let's start by defining one of the basic building blocks of time series analysis. So one of the important basic families of time series processes. This is the class of autoregressive models. In an autoregressive model, the meaning of the model is very simple. We have that the value of our random variable today depends on the value or the values of our random variable in the past. Why I say the value or the values? Because it depends on the type of autoregressive model on how many past legs we consider. So in an autoregressive model of order 1, if we consider daily observations, the value of today depends on the value of yesterday. In an autoregressive model of order 2, the value of today depends on the value of yesterday and the value of the day before yesterday. If we consider an autoregressive model of order 100, it means that the value of today depends on yesterday, the day before yesterday, and so on until 100 days ago. Okay, so we are keeping memory of the last 100 days. So what is important is that in an autoregressive model, the value of our variable auto-regresses, so it's a regression on itself for what concerns past observations, or if you have an anticipating process, for what concerns future observations. So, but it's always the variable with respect to itself. A stationary time series, because we focus on time series that are stationary. So we have already taken care of trends, seasons, and all those problems. We want to play with something that is stationary. We call this time series an autoregressive process of order p if the time series xt can be represented as the sum of p legs in the x quantity, so xt minus 1, xt minus 2, xt minus 3, up to xt minus p. All these legs have their own parameters, so phi1, phi2, phi p, plus a white noise component, wt. Okay? Now, this time series has some requirements. First of all, we want all the parameters, phi1, phi2, up to phi p, to be constant, so they don't change over time, they are constant. Phi p is trivially different from 0, because otherwise the pth leg will not be there. And for what concerns all the others, so they can be 0. So it's not necessary that phi 3 and phi 6 are different from 0 if our time series is of order 8. Okay, so you can have that some intermediate phi can be possibly equal to 0, because there is no memory, I don't know, what happened between day 5 and day 7 in the past. I don't know, it may happen. It would be strange, but it may happen. So this is what we require for our construction. And again, I repeat, we are considering xt to be a stationary time series that we can represent in terms of p legs of the x quantity itself. Okay? Very important. If our time series xt has a non-zero mean, we can always rewrite everything by reparameterizing the time series. That means that essentially we introduce a constant term alpha, an intercept. Exploiting the b notation, the b operator, we can introduce phi of b to represent the quantity 1 minus phi 1b minus phi 2b squared minus blah 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 until we reach phi p b to the power of p. And if we use this, an autoregressive process of order p can be easily expressed as you see on your screen. So it is nothing more than phi of b applied to xt, and this part is equal to wt, to a white noise. A time series xt in which the value of xt only depends on past observations, so xt minus 1, minus 2, up to minus p, is called a causal autoregressive process. Causality is extremely important in time series. We will not enter into the details, but heuristically, so in a very simple way, it just means that our time series does not depend on the future, but only on past observations. Because there is no limitation in time series, and in principle, we could say that the value of our random variable today depends on the value of tomorrow, the day after tomorrow, and so on. Now, this type of time series in finance is not particularly useful, also because you remember probably from financial mathematics that we play with non-anticipating quantities. So we don't want our process to depend from or on future values, but there is no limitation from a mathematical point of view. In any case, if the value of our random variable today, of our quantity today, xt, say, just depends on the past, we say that our time series is non-causal. Regarding causality, you find a lot of very interesting discussions in the book by Shamway and Stoffer. Here, I just want to show you a simple thing when we just focus our attention on a very basic autoregressive process, which is an autoregressive process of order 1. That is to say, when we can write xt as phi xt minus 1 plus a component wt. If we assume the parameter phi to be within the unitary circle, strictly within the unitary circle, that is to say, taking values between minus 1 and 1, but without taking exactly the value minus 1 and 1. Now, in that situation, it is easy to prove that an autoregressive process of order 1 is stationary, and I leave that to you as a very useful exercise. At the same time, when phi is in absolute value larger than 1, so when we are out of the unitary circle, then it is quite simple to verify that the process is explosive, because what we have is that over time it tends to grow and grow and grow, because phi is larger than 1 in absolute term, and it will explode in the limit. So it will reach values like plus infinity in the limit. Now, this process is, when it is explosive, it is clearly non-stationary. Now, a very interesting thing that we can notice is that the process xt equal to phi xt minus 1 plus wt can always be rewritten as the second process that you see on your screen. So we can just rearrange all terms and write that xt minus 1 is equal to 1 over phi xt minus 1 over phi wt. Now, this new process, since phi is larger than 1 in absolute terms, we have that 1 over phi is smaller than 1 in absolute terms. So what happened is that this new process we have defined is actually a stationary process. But at the same time, it's a process for which the value of xt minus 1 depends on xt. So the value of xt depends on xt plus 1. So this is an anticipated process. So it's a process that looks towards the future. So it's a non-causal process. So we can see that with this very simple example, we can already see that there are connections quite interesting in time series analysis between, for example, explosive processes and non-causal processes. But as I told you, we will not enter into the details. In any case, you can imagine that even if your process is stationary, if it is non-causal, so if it depends on the future, it is essentially useless from a statistical point of view, because in order to make inference about the future, you have to know the future, which is some sort of tautology, unless you want to reverse time and then you want to use the future to make inference about the past. But at least for what concerns me, I don't have that power, so I would not suggest to try to do that. Moving average processes constitute a second fundamental family of processes in time series. They are another important building block. Now, in a moving average process, what happens is that we keep memory of errors, of the noise. We are no longer saying that there is an autoregressive component in xt, but, for example, the value of xt depends on the value of the quantity Wt, our white noise, but also on the value of Wt minus 1, Wt minus 2, and so on. So in a moving average process of order Q, we keep memory of Q legs in the errors. On your screen, you see that the moving average model xt is of order q if we can write it like the sum of Wt plus theta 1 Wt minus 1 plus theta 2 Wt minus 2, and so on until we reach theta q Wt minus q. Now, as we did for the autoregressive models, we can introduce the quantity theta of b, which is again 1 plus theta 1b plus and so on until we reach theta qb to the power of q. And we have that in the moving average of order q, we can write that xt is equal to theta b Wt. Moving average processes are extremely useful, they can be extremely powerful, but they can also be quite tricky. I want to show you that with just a simple example. Consider the two processes you see on your screen. These processes are both moving average processes of order 1. But they are different because we see that in one process, the process xt, Wt is normally distributed with mean 0 and variance 25, while in the second one we have that Vt is normally distributed with mean 0 and variance 1. Now the point is that from an empirical point of view, these two processes cannot be distinguished. It's impossible to distinguish them. In fact, in analyzing data, the quantities we observe are xt and yt, not Wt and Vt. And in these two different constructions, we have that the mean and the variance of xt and yt are exactly the same. So how can we choose the appropriate model if at a certain point we have to estimate one of the two models? So is there a way to choose one of the two models? Okay, there is a way. We have to introduce the concept of invertibility. And in these two constructions, we will prefer the process that is invertible. Consider an autoregressive model of order 1 and assume that the phi parameter is within the unitary circle so that our process is stationary and all the rest. Okay? Now, what we can do is to start performing a series of substitutions. So we have that xt is equal to phi xt minus 1 plus Wt. Now, one thing that we can do, we can substitute to xt minus 1 its own definition, which is phi xt minus 2 plus Wt minus 1. And we can go on and on in all these substitutions. Now, if you do that, you can easily show that an autoregressive model of order 1 can be written as a moving average model in which Q tends to plus infinity. Why you can do that? Because the phi parameter is smaller than 1 in absolute terms. So every time you multiply the phi parameter by itself, and that happens a lot every time you perform these substitutions, that element here that multiplies the x will tend to vanish, will tend to 0. So what remains is just the part in the errors, and the part in the errors is actually the moving average part that, with all your substitutions, will tend to have a Q growing towards plus infinity, depending on how many substitutions you perform. Okay, in a similar way, you can show that a moving average model of order 1 can be represented as an autoregressive model of order p, where p tends to infinity. It is exactly the same stuff, so you just rearrange the terms and perform substitutions. Now we say that a moving average process is invertible when it has an autoregressive representation, an infinite autoregressive representation, and in particular a causal autoregressive representation. So if you have two theoretical models, what you will try to do is always to choose the model that leads to an invertible construction. So if you are curious, in our previous example, you will choose the process xt and not the process yt. Why? Because under the process xt, we have that if we represent this model in terms of an autoregressive model, we will have that the process as a parameter 1 over 5, which is within the unitary circle, it is stationary, it is causal, and all the rest. And so if we perform all our substitutions, we will end up with a moving average model of order 1 that can be represented as a causal autoregressive model of order infinity. An ARMA model of order P and Q is nothing more than a model that combines an autoregressive component of order P and a moving average component of order Q. We can represent an ARMA model PQ in many ways, but the most convenient way is what you see on your screen in terms of the operators phi of B and theta of B. In the next lesson, we will give more details about ARMA models, okay? So we will enter into their properties, into the modeling, into the estimation, and we will see that an ARMA model is already a quite flexible tool if you learn how to use it. We will see that for our quantitative risk management purposes, ARMA models are already quite a successful tool to be used. Now, before entering into that lesson that is specific on ARMA models, I want to close this lesson by letting you notice one important thing, which is something that does not only apply to time series, but it's something that is very important in general in statistics, and that for us will be one of the different topics under the big umbrella of model risk that, as I told you from the very beginning, is an important risk that we have to consider. That is to say that the model we are using is wrong, is not reliable. So consider the following simple model. Let's assume that xt is such that it can be represented as 1/2 xt minus 1 minus 1/2 wt minus 1 plus wt. Now, if we use the ARMA representation, we see that we have an autoregressive component in xt, so we have xt and xt minus 1, so this is an autoregressive component of order 1, and we have one leg also for what concerns the moving average part. So this model is a combination of an autoregressive order 1 and a moving average of order 1. So in principle, it is an autoregressive moving average model of order 1, 1, that is to say, an ARMA 1, 1. My question for you is this really the case? As you can imagine, the answer is no, otherwise I would not have asked. Now, in order to see that, we can use the phi b and the theta b representation. So what you can see is that we can write the process as on your screen. on the left-hand side we have the autoregressive component, while on the right-hand side we have the moving average component, and both components are of order 1. Now it is quite simple to observe that the terms in B can be simplified. And here you see the power and the beauty of the notation we have introduced, which is not just a mathematical sadistic choice, but it really helps in playing with time series. And we discover that at the end of the day, our ARMA 11 is nothing more than a simple white noise. So we were actually complicating water. So it is very important to always think critically about the models that you are trying to fit to your data. Do they make sense? Don't be fooled by data, because if you try to fit the model, the ARMA 11 model that we have just considered, probably you can find out something that in appearance can make sense, but at the end of the day is totally useless, and you are just introducing model risk in your framework.